Okay people, going to have a look at the 2018 higher level section 8. So A1 is an axonometric question, and just having a quick look at it there. Just to be careful about what you're given. You were given this bike stand here, so I'm going to just number these 1, 2, 3, 4 and 5. So when they project in, I'm going to just project this forward another bit now, because the one that's given here is the one on the ground at the back. Now again, I'm going to just throw a few colours in this to help people understand it, but they're after giving the back leg of the fifth one. So I'm projecting forward here so I can find these points on the ground. So I'm going to draw this. I'm going to draw those supports inside here first, and then I'll do the roof and the frame around it afterwards. So we now have this point here on the ground for the fifth one. So what I'm going to do there is I'm going to just project forward and find the points on the ground for all of these. So those 2 points are for the fourth, third, second, and first. Okay, so they're all the points that are on the ground. Now what I'm going to go now and bring next is I'm going to just project there. So this is the high leg at the back. Okay, so the point up here. So I'm going to find them next. So they've already, well, it's just coinciding here, but we've got the line to work with on that. So I'm going to find these next. So there is 5 is found. So 4 is here. Now I'm going to leave out some of these lines here now just to reduce the clutter. Okay, just so you can see where that one came from. So, and I'm going to draw these in. Okay, so we have found now the 5 back legs there. So my next issue here now, I'm going to project down the line that contains all of these front legs. So they're all at this height. Now, the problem here now is these sloping down bars here. The height, we knew the height of that off the ground because we were given that. But what we need to do there now, I think the easiest way to do this is I'm going to take a height from this side view. I'll just put this in red so you can see it. I'm going to just call that H. We need that height. So I'm going to take that height. Now since this is a side view, so a height in a side view is the same height in a front view, which is over here. I'm going to step that up there and take them across parallel to the ground. So I'll just mark these bigger than they need be so you can see where they're coming from. So that now is the height of the front points in all of these. So now I can project these down. So that front point must be on this line here. Okay. So that's 1, or that's number 5 really. Number 4. Number 3. Number 2. Number 1. Okay, so there we go. 5, 4, 3, 2, and 1. And then they return down to the ground. Like that. Okay, so that is our 5 bike supports. So now we need to do the shed or shelter there. So we know they've given us the side of that there, which was a big help. So I'm going to find the highest point here out of the front. Now I just need to project, because I'm projecting it down from the side view there, and then I'm going to project it down from there. Okay, and that point is here. Now it's coincidental that this projection line here brings down the top height of the front of the shelter, but it also coincides with the back of the supports as well. That doesn't make a difference, it's just a coincidence. Okay, so that there is the point that I'm after finding, and I'm going to use parallel lines here now as well. So the back lower down point, I'll draw this a little bit heavier than I normally would, just so you can see it. So the back low point, now I'm going to put here L for low, H for high, and that middle line there represents the middle steel support in the shelter. So the low one comes down to here. Okay, the low one comes down to here and there. We already said the high one is coming down from here and there. So that gives us this line in the shelter. And I can also heavy in then properly that, this, and now the next thing I want now is, and just be careful with this here now, they did not give us the projections in of the leg supports here. These 2 points on the ground are coming in here. Okay, so those points on the ground, so the front one, when I bring it down from here, so here's my front support, here is my back support in the side view, so I mark that. So the back one goes up to there, the front one goes up to here, and all I'm missing now is the middle support there, which is where that, I'll just put an M on this line here. I'm missing that middle support now, so I will just project down that line, and that locates it, and we know it's parallel. And that, I think, is that. So it says a line joining Y to B represents the straight line path of a football. Okay, so a line joining Y to B represents the straight path of a football. So show the point of impact of the ball with the glass roof in the axonometric view. Okay, so basically, where would that ball pass through or impact with the glass roof? Now, look, what I'm going to do there is I'm going to just do this in green so you can see. So look, if I kicked a ball from B going in the direction of Y, it is going to impact the roof here. That is where it is going to impact it, because I'm going to just do this off an in view. So we can draw in the path of the ball down here. So from Y to B is the path of the ball. So I'll just put that in on green so you can see it. That is the path of the ball, and I'll just put an arrow just to show the direction that the ball is traveling in. And where does it impact the roof? Well, we know that it impacts it here in the side view. So if I project that down, to here, that there point P is the point of impact. Just put a little arrow there to show that that's coming down from here. So that's the point of impact in the side view, but we want to show it on the axonometric, and there it is. Now, second question. So, fishermen skew lines. So two fishing rods, AB and CD. So determine the projections of the shortest horizontal line. Now I am going to highlight here just one thing. Horizontal line, okay? Because the shortest horizontal distance is different to the shortest distance. The shortest horizontal distance needs to be horizontal in the elevation. So it's not going to be at an angle like that. It is going to be horizontal. So how you go about this is the same in whether it's shortest distance or horizontal distance. The first steps are the same. We want to create a plane where I'm going to go parallel to AB. It doesn't matter which line you choose to go parallel to, so I'm going to just pick AB. I'm going to go parallel to AB and horizontal from D. Giving me here a point that I will call X. Okay, and I'm going to mark now that that and this are parallel. So that's parallel to AB. So I'm going to bring down point X to plane. And I want to do the same parallel again. So parallel to AB. Parallel to AB. So I want to go parallel to AB from C. And this is X now found in the plane. Because X has to be down here, and we want to do the same parallel in both. So I will just join there now. X to D. No. X to D is the angle that we want to look at. DX, horizontal line. Now, if I look at that angle, DX, now I'm going to keep the XY line. I'm going to draw down on top of my construction work here now, because all I wanted to find there was the angle to look at. Okay, so now that I have my angle to look at, and I'm going to project these forward. So D and B, A and C. Okay, and really what I wanted there was that angle. And the XY line I'm going to put at 90 degrees obviously to them, but I'm going to keep it back here because now that I found the angle to look at. So here's my XY line. Okay, and I want now draw that auxiliary view there, and these lines should appear parallel, so I'm going to just project these down to take some heights. So again now, the rule with auxiliary views always remains the same. So I'm projecting from plan, so from the last XY line back. So my height for A, or my distance for A and C, B, and finally D. Now this view, the lines should be parallel. If they're not parallel, you've done something wrong, so stop and be careful now, don't try and work wrong. So A joins to B, C joins to D, so you can see they are parallel. Now if I wanted the shortest distance, I would be taking another auxiliary perpendicular to them, but this is the point I was making earlier on. We want the shortest horizontal line, so we need to look along parallel to the ground. So here is the angle of the ground. So we want to look parallel to the ground to see the shortest horizontal distance. So C, A, D and B, XY line. So XY line goes here, and again remember the rule, I am projecting from here, so from the last XY line back is my distances. So C should be the closest one. There's A, which is the furthest away. Just be careful now you don't mark a distance on the wrong line. D. Okay, so I'll just index these B, C, A, and D. So when I join these now, they should be crossing. So we've got AB, CD, okay. Now the point that I'm looking for is this point here. where they appear to cross. No, I know they appear to cross in the same way as like these pencils appear to cross there, but they don't in reality. So this is the shortest distance, but we need to bring that information back. We need to bring that information back to the plan and elevation. So I'll just leave it in green here. Switch to set squares for this. So there's our angle to project back, and that is our shortest horizontal distance here. Now you could find that point on AB and find that point on CD and project back and project up. I would have a slight preference, because when we were setting up this view, we took, I'll just demonstrate with A, we took our distances from A from here, so they're all heights that came from elevation. So what I can do now is I can take this height off the ground here and step that height up here, and that is a more accurate way of bringing my shortest horizontal distance back. And to bring it to plan, then it's here on AB. I won't draw this line down now. It's here on AB, it's here on CD. So the plan of the shortest horizontal distance is here. Now that would have given me the same answer if I brought this point back onto AB and up and back onto CD and up. But if you're any way out, and it's easy being mill out, it can sometimes give you a sloping line up here when it's supposed to be horizontal. Okay, now the second thing there says, so determine the projection of the shortest horizontal distance is done, and determine and indicate the distance from this line to the horizontal plane. So determine the distance from the horizontal plane is just to indicate it from the horizontal plane. Is kind of a test of terminology there really. So it's like there to there is the height. Okay. A3. Now again, this is a curved support pillar is based on a parabola. Okay, so we've got the vertex and a point on the curve. So our curve is coming this way, and there's the focus of the parabola. Now, whenever you're given a point, let's see if I take this distance here. If it's a parabola and the construction is set up for you, now you could work with your own distances, but generally you can presume that, you know, it's a quarter, a third, or a fifth. You can see there. So that was exactly a fifth, and it's the same in this direction here. Just need to be accurate there, because if you're 1 mil out and you step it 5 times, you can be 5 mil out. So here's my distance here for this one. So this will work out being 5 as well, because this is back to our junior cert parabola construction. Now I'll put that on another video anyway at some stage, but so we're just constructing a parabola in a rectangle. So those go to the vertex, and they'd already found the first one, so it's second to the second. So those are all our points starting here, and And there's our parabola. So the curved support pillar is based on a parabola in a rectangle. Draw the parabola. Okay, so this now being a parabola, we know that point to the focus would be also, like, I could, and I will tie this in even though it didn't ask for it even, but that distance from the point to the focus would be the same to the directrix. So like if I want to there now, I could just find the directrix here for this. It would be here, that distance, that would be the directrix there, DD. So we've got our axis. Just to kind of link it more to the you know, to the other method, the eccentricity and axis method, and since that is the directrix and it's a parabola, the line of eccentricity is equal to 45 degrees here, and all that, just to link it in with, you know, with the bigger picture. And if I came straight up from the focus there, it would be tangential to it and all that. Just linking it to the bigger picture there. But what they asked for here anyway is that F is the focal point of the parabola. Point P is anchored to the bridge. Okay, and the line PF is one cable. Okay, so I'm going to put this in blue here now. So the line PF is one cable. And the second cable is inclined at 25 degrees to a tangent at P. Okay, so construct the tangent at point P and draw both cables. Okay, so the rule with drawing a tangent to a parabola, so let's say you've got a parabola here. I'll just sketch it over here for a second. There's the parabola, and here's your focus. And if we want a tangent at P, you join to PF, I'll extend that, you join to the second focus or focal point, which is at infinity. F2, I'll just put the infinity symbol here, and which is parallel to the axis. And we want to bisect this angle here now, and that's going to give us the tangent. I need to apply that construction over here. So so the second focal point would be at infinity, is the rationale or the thinking behind it. I'll do this in a color there now just to make it a bit easier to see. Okay, so I'll do it in red. So there's that one, and there's our cables there. So I'll just extend this out as well here in red. So I want to bisect this angle here, or that angle there. Do that with a compass. So again, step out a distance. Don't do this too small now, do it a bit bigger, you know, do it big so that it's more accurate. Just make the compass a bit bigger, so two equal distances again. Swing an arc, another arc. Okay, now this is the bisector of the angle. So there's my tangent. I'll just put a T on that. So I have found the tangent here now, T for tangent. That is the tangent. And the cable stay is 25 degrees more than that. So you need a protractor there then for this. So there's our protractor. Now 25 degrees angle with the tangent. So I'll just line that up with the tangent. So 25 degrees more is there. So that's the angle. For the second cable, I'll just extend that off over here to tie it down. Okay, now I know that finding the directrix and putting the eccentricity and all that stuff in on this, but really it's better off to try and understand the big thing on conics rather than just answering the questions in isolation. Like, you need to see the big picture. So construct the tangent to point P and draw both cables. So that's that sorted. So finally there now, the graphic shows a spider cam used for aerial coverage of sports events. It is supported by 4 cables. Okay, so the drawing shows the projections of the cables. Find the dihedral angle between OAB and OAD. So OAB and OAD. So again, OA, I'm going to put a color on this. OA is the line of intersection. It's on both triangles. So I'll just color that in good and bright there now so people can see it. So we need to find the true length of OA and look along it to find a point view. So normally here, a person wearing a sombrero on their 2 toes, we need to walk over here and look in perpendicular to see the true length of that. So that's my angle for OA. So I'm going to put an XY line just over here. And I want to project these up 90 degrees, so we're going to need definitely A. We're going to need O, which is down near the ground. D. B. And C. So again, our rule on auxiliaries applies here now. So we are projecting from the plan, so from the last XY line back. That is the rule. Now ideally I would find exactly beneath this, but okay, so that's my height for O. Now I'm going to just mark these here. Just project these down so that I can take absolutely vertical heights to be accurate. So A, and again just be careful now you don't mix these up. So A, and I'll just go a bit slower again there because I'm trying to teach using these questions as opposed to just answer the questions. So AO, that is the true length. Just put in there TL. Now that is what we were looking for, but I also want some more points as well because we can't find a, so D is this height. We can't find a dihedral angle without a point on each of the other triangles or planes. So C is here. Okay, so I'll just index them again. There's C, B, O, D, and A. Now, do I have to join them up? Well, I will okay, so it's A goes to D, D to C, C to B, and back to A. Okay, so that now is the true length of the line of intersection, so between both of them. So I want to look along that now and get a point view of it. So I want to look along that. I'm going to put an XY line here pretty close. So bring our points, project them out again, that angle. Okay, now the reason we're going to be getting a point view of this is because by putting the XY line parallel to AO there, when I take my distances here, now we're projecting from here, last XY line back. So when I take that distance here, for A and for O, it's the same distance. So when we look along that true length, they're both the same distance and they're both on that line. So that now is a point view of O and A. So now we need some more points. So I'll bring D. Now really I only need D and B for what I'm doing here. Okay, so D is there. B is here. So this is my dihedral angle. Okay, so that's the dihedral angle between OAB and OAD, and that's edge views then of both planes. And then determine the angle between the cables OA and OB. Okay, so they want the angle between the cables OA and OB. Now really what they're asking for there is the true shape of this triangle. Okay, so they want the true shape of OAB. So just color that in there to again to help us understand it. So the angle between OA and OB, true shape of that. So now a really quick way of finding that, the true shape of OAB, because if I color that plane in there, this is it here. We have it here as an edge view. That's an edge view. So if I was to look down here at this angle, perpendicular, so I'll just draw a person looking down there. So if I was to look down there perpendicular, I will see a true shape of that. And if you already have an edge view of it, that is the quickest way to finish this off. So just set up there my set squares to go. Okay, so that's our angle. So I want to look down here. Going to put an XY line there really close. Okay. So that was my XY line, that was XY1, XY2. 2, and I'm putting in x, y, 3 here. So I'm looking down here, so I'm projecting from here, so the last xy line back. Projecting from your last xy line back, so my distance for A my distance for O. Make sure you have a good sharp point in your compass for these. So A and O. And finally my distance for B. So that there, AOB. And again, just to link it back to our plan here, just colour a tiny bit in. Okay, and the angle they wanted was the angle between OA and OB, so it's the angle at O is what they were looking for. So I just marked it in there with a little theta. Okay. Now there is other ways you could do it. I mean, I could have taken a horizontal line from A across here to OB, horizontal line here, find that point at OB, and I could have taken an auxiliary and got an edge view of the plane down here and looked at 90 degrees to that. There's other ways of doing it, but if you've got an edge view in the dihedral angle, it's just quicker to take one more view and you have it. So yeah, that's 2018 sorted. So I hope that's of use to you.